Today we're going to talk about phase diagrams, and most of this will actually be review for you since you've probably discussed phase diagrams in the past. There's two types of phase diagrams. There's a heating curve and a cooling curve. Today we're going to focus mostly on heating curves, although the opposite is going to be true for cooling curves. What a heating or cooling curve shows you is how a substance's temperature changes over time when constantly losing or gaining heat. All right, so let's look at what a heating curve would look like. So you can see over here, I have some axes drawn for you. This is temperature and this is time. And we're drawing a heating curve, so we're going to be constantly gaining heat. We're going to start today talking about water, and probably that'll be the only example we ever really talk about. And we're going to start with ice, below the freezing point. When you add heat constantly to ice over time, it's going to increase in temperature until you reach the melting or freezing point, at which point, even though you're still adding heat, you're going to see a plateau. During that time period, it's actually melting. So even though you're still adding heat, you're not going to see a change in the temperature because it's using that heat energy to change phase. Once it's all changed into liquid water, it will once again begin changing in temperature, and that'll continue until it reaches the boiling point. Once it reaches the boiling point, it's going to use that heat energy in order to boil and change phase. And then if you continue to add heat, it'll actually heat up the steam, like so. So what we had down here is the solid phase. Here was the liquid phase, and up here the gaseous phase. This plateau was the melting point, which for water would be 0 degrees Celsius. So this would actually be in Celsius. And then up here, this would be the boiling point, which for water would be 100 degrees Celsius. What is happening to temperature at the sloped sections, which is the question over here on the right? So the slopes are those that look like slopes, those that have a slope greater than 0. And what's happening is temperature is actually increasing. Where at the plateaus, and we're talking about these flat sections here, the temperature is going to remain the same. And that's not because we stopped giving it heat. It's going to be constantly gaining heat. Why it's remaining the same is because it's using that heat energy to actually convert to a new phase. So we've been using this word temperature for a little while, and I think we've probably defined this before, but let's write it down again. But temperature is the average kinetic energy of a substance. In this case, we're talking about water. So we want to talk about this same diagram in terms of kinetic and potential energy. If you recall, kinetic means the energy of motion. We're talking about molecules speeding up if temperature is speeding up. So if temperature increases, the speed of those particles is increasing. Let's draw our phase change diagram again, our heating curve for water. Looks something like this. And we're going to look at what happens to kinetic energy and what happens to potential energy in each line segment here. Whenever temperature is changing, temperature you can think of as being equivalent to kinetic energy. So if temperature is changing, kinetic energy is changing. This first line segment, when we were just heating up the ice, we were actually changing the temperature. So that means there was an increase in kinetic energy. The potential energy in that line segment remained the same. The next line segment, this plateau where we were melting, we were still adding heat, but the temperature wasn't changing. What was changing was actually the position of those particles. They were moving from being packed tightly in a crystalline structure as a solid to moving apart from each other as a liquid. I like to think of potential energy as the energy of position and not so much stored energy. I know that's how a lot of people define it, but if you think about an example of, say, a ball at the top of a hill, this ball, prior to me letting it go, has a lot of potential energy. And in the past, you've thought of it as stored energy. But the reason why that ball has the energy it has is because of its position at the top of this hill. And as soon as we let that ball go, it's going to roll down the hill because of its position, converting that potential energy into kinetic. So we can think of it the same way when we talk about phase change at this lower plateau here where it's melting. Those molecules are changing their position, so they're changing in potential energy. They have a different position now that allows them for greater movement. And the next line segment, that's where we have our liquid water, and it's going to be increasing in temperature. Again, when temperature changes, it's kinetic energy that's going to be changing. So this plateau, we are going to see a change in kinetic energy. And again, in the next line segment, the plateau, we're going to see a change in potential energy. So if my description of the change in position being potential energy doesn't help, you can recall the plateau, it's potential, plateau, potential. Where with the sloped portion, since we're changing the temperature, we're actually changing our kinetic energy. Since this is a heating curve, the kinetic and potential energy in each of these line segments would be increasing. Vice versa would happen with a cooling curve. They would all decrease as you go through the cooling curve. So kinetic energy, if we were to define that, would be the energy of motion, and it's going to change at the slopes. The potential energy is the energy of position, and that's going to change at the plateaus. So now we're going to be doing some stuff you probably haven't talked about before. We're going to talk about how you can calculate the heat in each of these different scenarios. In order to really understand what's happening here, you're going to need a couple of things. You're going to need a definition of the heat of fusion and the heat of vaporization, and we're going to talk a little bit about another constant called the specific heat capacity. All of these things are listed in your reference tables, so you'll probably want your reference tables, though I'm going to bring in those tables that we'll use as images now. So the two tables you're going to need are Table B, which is on the front of your reference tables, which includes this constant called the heat of fusion. This is the heat of fusion for water, and what it is the amount of heat that you need to convert a gram of water from solid to liquid or liquid to solid. We'll talk more about that in a minute. And then heat of vaporization would be the amount of heat, which is measured in joules, just like up here, per gram of water required to convert from liquid to gas or gas to liquid. And then this last one here is the specific heat capacity of water. And this is expressed as the amount of heat per gram of water to change it 1 degree. And this is Kelvin, but Kelvin degrees and Celsius degrees are the same, and we'll talk more about that in a little while. Over here on the right, I've brought in part of the very last table on your reference tables, the back. There's a section titled Heat, and there are 3 equations you may use. Q represents heat in each of these. M represents the mass in each of them. And then there are different numbers for each of these after that. So this first one has this big capital C, and that is the specific heat capacity. And what they've done is they haven't included what that constant is here. You have to know to go back and look here. I think it's a little unfair. Why wouldn't they just include it right here? But they haven't. So you would have to go back and find it on table B. And then delta T in that same equation is just the change in temperature. And then the other 2 equations have different constants. HF, the heat of fusion, which again you have to go back and find in table B on the front. And HV, which is the heat of vaporization, which again you have to turn to the front and find that. So what is the heat of fusion? The heat of fusion is the amount of heat, so that's joules, required to melt, or actually to freeze, melt/freeze 1 gram of water. So if I had 1 gram of water, I would need just 334 joules. If I had more than that, I would need to multiply that by its mass. So that's what this middle equation is here. So let's look at this first one. We have how much heat. So in this one, they're looking for Q, and I like to write all over mine so I don't forget, is needed to melt. Okay, so you have to recall which equation to use. My suggestion, I would actually, and it would be a good idea to do this at least once, and I'm going to have you do it in class, I would associate each of these equations with your phase diagrams. Whenever you have temperature changing, which is where you have your slopes here, that is going to be Q is equal to MC delta T, because that's where we have a change in temperature. Okay? The plateaus, for this lower one, since this lower plateau is where we have freezing, for that one, you're going to use Q is equal to MHF. I like to think of that F as the freezing point, because this lower plateau is the freezing point. The upper plateau here, that's the boiling point where you have a vapor. That's where you're going to use Q is equal to, I'm not going to fit it there, MHV, or vaporization, heat of vaporization. So since we're talking in this question about the melting, which is this freezing point, this lower plateau, we're going to use this equation. So we're going to use Q is equal to MHF. They've given us the mass, so this is M. We're looking for heat. Okay, so we're going to be solving for Q in this equation. We have M, so we need one more thing. We need HF. If you recall, HF is the heat of fusion, and that number is expressed here in table B. So we're going to be going from table to table and back and forth. So we're going to substitute in M, which is 20.40 grams. And we're going to substitute in HF, which is 334 joules per gram. Since grams here is in the numerator and here in the denominator, they cancel out. Our final units will be joules. So when we're all done here doing our math, we're going to express that in joules. So now we just plug this into our calculator, 20.40 times 334, and you get 6,813.6 joules. Make sure you include your units. I don't want any naked numbers. That would be shocking. All right, next question. How much ice will melt? So again, we're talking about this lower plateau, so we'll be using Q is equal to MHF. If 2,500 joules of heat is added. So this is actually Q. So this number is Q. And we want to know M. Okay, so we're using Q is equal to MHF. And in this case, we're looking for M. So there's a couple ways you can go about this. You can plug in your numbers and then solve for M, or you can solve for M first. I'm going to do it the way I assume you do it, even though it wouldn't be my preferred method, and I'm going to plug in my numbers first. So I said Q is 2,500. M we're going to be looking for. If you insist, you can change that to an X. I like to leave it as an M so I remember what I was looking for to start with. And then HF again is 334 joules per gram. To get the M alone, I would divide each side by 334 joules per gram. My joules are going to cancel out, and I'll have 1 over grams, which works out to be just grams. These guys cancel out, and I'll be solving for M, which would be grams. So we do 2,500 divided by 334, and we get 7.485, and our units are grams. All right. The next couple of questions are going to have to do with heat of vaporization. So let's define the heat of vaporization as the amount of heat required to boil. Now, boil would be in the heating curve. Condense would be in the cooling curve. 1 gram of water. Oop. I missed my F there. All right, so let's move this up a little. And let's look at these questions. How much heat is required to boil 20.40 grams of water? So because we're talking about boiling, that means we're going to be talking about that upper plateau. So to look back at our little drawing over here, that's this upper plateau, and we're going to be using Q is equal to MHV. All right, this is our M. Okay, we're looking for Q, or heat, and we need HV. HV, if you remember, is the heat of vaporization, which is expressed in Table B as 2,260. So we'll substitute those in, 20.40 grams, and then HV from Table B is 2,260 joules per gram. Again, our grams cancel out, leaving our units being joules. We multiply those two numbers, and you get 46104 joules. All right, next one. They want to know the amount of water, so we're looking for M. We're boiling, so once again, that upper plateau where we use the equation Q is equal to MHV, and they've given us our heat, which is Q. So we're going to plug those numbers in, 7910 joules is equal to, we're looking for M. HV is this constant again, 2,260 joules per gram. In order to get the M alone, we'll divide each side by 2,260 joules per gram. Our joules cancel out. We get 1 over gram, which is just grams. So we do the math, 7910 divided by 2260, and you get 3.5, and not forgetting our units, grams. So that's how you would do any questions having to deal with those plateaus. This last question is a question dealing with temperature actually changing, which you can see from the question. It's going from 20 to 80 degrees Celsius. So if we were to go back and look at our little graph here, that would be in this region of the graph, which means we're going to use this equation. Anytime you have a temperature change, you're going to use that equation. Oops. So the equation we'll use is Q is equal to MC delta T. Now reading our question here, we have 25 grams, that's M. They want to know the joules, which is Q. And the temperature change is going from 20 to 80 degrees Celsius. So whenever we do delta T or delta anything, it's actually the final temperature minus the initial temperature, which in this case would make that 80 minus 20, or 60 degrees Celsius. So our delta T is 60 degrees. So we have M, we have delta T, we're looking for Q. What's this C? The C, if you recall from down here, is the specific heat capacity, and you need to remember when you have that you need to look that up in Table B. It's actually a constant, 4.18 joules per gram degree Kelvin. So let's plug all of that in. M is 25.0 grams. C is 4.18 joules per gram Kelvin. And then our delta T that we figured out is 60. Since we're talking about a change in temperature, a degree in Kelvin is the same as a degree in Celsius. So those two units are going to cancel each other out. This grams is in the numerator, that's in the denominator. So our final answer will have the units of joules. So now all we need to do is multiply. And when we do, we get 6270 joules. Don't forget your units, no naked numbers.